Yes, hello everyone. Mm-hmm. 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 Yeah, but actually, we can do this only at the end of semester because I have another 4 hours of teaching of another course, so it should first end and then we can try to explain. Hmm? Yes. And actually, I need to think it. It seems to me that we need 3 extra lectures, and we have only 2 extra slots near the New Year. But probably the last lecture can be on Zoom if you wish. So I need to count this carefully and just then decide. Yes. So I have 2 hours of mathematical physics and then 4 hours of conformal field theory. So on Tuesdays and Thursdays. Mm. And you come here only on Tuesdays and Thursdays, right? Mm-hmm. So maybe if you wish, we can also try some other day, but or is it generally inconvenient for everyone? Uh, so for me, maybe not Wednesdays, but Mondays and Fridays are generally okay. It depends on a week. So maybe we can discuss this later, or you can discuss yourself. Mm, mm. Or if it is Wednesday, then it should be in the morning. So. Maybe I just try to all the possible options and we decide then. Mhm. Okay, so shall we start? Yeah. Uh, do you have any questions about last times and about the problems? Mhm. Uh, mm. Okay, so let us talk a little bit more about the wave equation. First, in 1 plus 1D. Mm. So it is this UTT minus UXX equals to 0, and we know that if there is something like this, it can be solved by u of t and x equals to some f plus of x plus t plus f minus of x minus t. And if we have this, we can check the following. We can check that this u also satisfies this equation. And u of u of t plus some delta t x plus delta x plus u of t minus delta t x plus delta x minus u of so let me check that it's correct. No, sorry. I'm writing something stupid. This one. Maybe it's fine. Oh. So let us check that it is true. Namely, substitute here first f plus, so it will be f plus of x x plus t minus delta t minus delta x plus f plus of x oh maybe no so let's see. Oh no, sorry, I'm doing something stupid, and now so let us better draw some picture. So it is a plane with coordinates x and t, and we change we choose some points like origin like 0 to 0, and consider consider the following 4 points. One is here, another is somewhere here. So, coordinates of these points are x0 at this point x0 plus some a, t0 plus some a. Here it is x0 minus some b, t0 plus b, and this point is x0 plus a minus b, t0 plus a plus b. So in principle, if we and now we take this u at these 4 points with the following signs. This one should be taken with plus, this one also with plus, and this should come with minuses. So if you now write the values of these functions at these corners, we can see the following. So that here we have so in the same picture. Here we have f plus of x0 t0 plus f minus of x0 t or t0 x0 0. Here we increase both t and x, and we will get f plus of t0 plus x0. Oh, no, write x0 minus t0. Here we get f plus of x0 plus t0 plus 2a plus f minus of x0 minus t0. Here we get so here we get f plus of x0 plus t0 plus f minus of x0 minus t0 minus 2b. And here we get f plus of x0 plus t0 plus 2a plus f minus of x0 minus t0. Oh, so it is f minus x0 minus t0 minus 2b. And now if we again take them with the signs plus, minus, plus, minus, then we see that this term cancels with this one. This term cancels with this one, and these two terms also cancel. Right. And this one as well. Because when we move along this 45 degrees lines, only one of two summands change, and if we take this alternating sum, then the final answer should be 0. And so there is a statement that a solution of the differential equation is also a solution of a difference equation, and actually of an infinite number of difference equations which live on different lattices. You see, because it is kind of a second derivative in this direction, in principle it should be the value of function here minus 2 times value of function here plus the value of function here. But since we subtract x derivative, like t derivative and x derivative, this intermediate term cancels, and so Laplacian operator was like this. Uh, plus 1, plus 1, plus 1, plus 1, and here was minus 4 in this point. And this discrete wave operator is plus 1, plus 1, minus 1, minus 1. And here it is 0, because because intermediate part of discrete second derivative cancels. So it's a very simple observation, and so it is a kind of different equation. But we can also make an observation that if we construct some closed line which consists of this 45 degrees segments, for example, this one. So if we construct something like this and also take alternating sum, plus, minus, plus, minus, plus, minus, plus, minus, then this sum will also be 0. So this is also 0. And now we can understand from this perspective why it is bad to formulate boundary value problems for the wave equation, because it satisfies this discrete equation, and so if we take points on the boundary, then it gives restrictions on the boundary conditions. For example, if we have a square of size a by a, then we have such kind of parallelogram which tells us that well, I'm going it wrong. So there is this parallelogram, or not parallelogram, but a rectangle, and we see that there is a condition that alternating some of these boundary values should be 0. And if it is something like 2 by 3 or some other irrational number, we can find such 45 degree line reflecting from the sides of this rectangle, such that there is a non-trivial condition on the function. And
I don't understand what is that the concatenation. What is like that yes, that one.
It's a statement that we take some, if we take any closed line which consists only of the segments and then go 45 degrees, then the sum should be 0 if function satisfies the wave equation, two-dimensional wave equation. Is it fine? Something irrational, or
We take as the domain which is in a code, for example. Then the boundary properties are opposed.
well, it depends on whether you can. No, it I think the answer is that it is always non-low-posed because if we have this boundary problem for this for this particular domain, then you can find some other domain which is infinitely close to this one, so that for that domain this problem is not low-posed. So there is no continuity in the initial conditions in some sense. But, so mm,
me that in case we take the cone, okay, we
mm,
can immediately get the solution with a single point in the cone by its projections by the values in the boundaries.
what do you mean by corner? Do you have another boundary of this corner or not?
No, infinitely.
No, in this case, of course, it is fine because you just have this formula. It's enough to say that on one boundary, one of these functions vanishes, on the other boundary, another function vanishes, and you just read them from the boundary values. So. Yeah. The question is what happens if you consider some closed domain like this. So, and yes, so in that case, if you add some other boundary to this corner, then of course its values on that boundary should be defined by the values on these boundaries, and so, so in this sense, it is a super ill-posed problem if you add another boundary. Uh, so, so it was some remark which I don't know if it is useful or not, but just for me it was funny to realize that this that this continuous equation is equivalent to a discrete one. So first I saw it at the level of the grand function because if you have something like 1 over cosine of px minus cosine of py, it can be rewritten as 1 of sine of like py minus px over 2 times sine of py plus px over 2. So if we try to solve the discrete equation using green function, we see that we can choose integration variables from px and py to have some half difference and compute the integral separately in one variable and in the other one. And we kind of get the same answer. And if you look more carefully, it is just clear from the equation that its solution solves also in the discrete one. So, but now a little bit more useful remark. Are there any questions about this? So another remark is what to do if we have some a segment and non-trivial boundary conditions. So let us consider this problem. X equals to 0 for x from 0 to L. And so we have some initial condition which can be taken as u of 0x equals to u t of 0x equals to 0. And the boundary conditions. U of a of t0 equals u 0 of t, maybe. Well, v0 of t. And u of tl equals to vl of t. So we have a string on a segment from 0 to L, and uh, and here we have v0 of t, some varying coordinate, and here is the L of t. So how to solve such a problem? So we can reduce it to a problem with zero boundary conditions, but with non-trivial right-hand side. So, namely, let us consider u tilde, which is equal to u minus v0 of t times 1 minus x plus vl of t times x over no, L minus x no, 1 minus x over L, and vl of t times x over L minus vl of t. So if we now substitute this into the equation, so so if we now substitute into the equation, we say that u t tilde minus uxx tilde equals to minus v0 to primes of t 1 minus x over L minus vl to primes of t x over L. So it's right hand side of the equation, and now boundary and initial conditions for this u tilde. U tilde of TL equals to u tilde of t0 equals to 0. This is precisely what we wanted. And u tilde of 0x will equal, so if original function was 0, then we should just look at this extra term. So, and this equals to v0 of 0, 1 minus x over L. X over L.
We should have also a minus at v0, 0. We should also have a minus at v0, 0, right? Because u tilde is minus minus, and so
Yes, and Sorry, actually, I've failed. Uh, Oh, sorry, I did this wrong because we cannot put here 0 because otherwise it will be inconsistent with boundary conditions because it's in contradiction. We should have u0 of 0 equal to something. Uh, from one side because it is v0 of 0, and here we are trying to say that it is 0. We cannot do this. Yes, but we can consider more general situations. So we should have here some functions u0 of x and t of 0 and x equals u1 of x. So sorry, it is so it is u0 of x minus this one, and the same for ut prime of 0 and x equals to u1 of x minus v0 prime of 0 1 minus x over L minus v L of 0 x over L v L prime of 0. So just trivial computation. So it tells us that this problem with time-dependent boundary conditions is essentially equivalent to a problem with the right-hand side. And we can apply the same for the other equations. For example, for the heat equation, we can put here ut minus uxx and do absolutely the same, as the number of initial conditions will be a little bit smaller. So this trick always works. So maybe for now that's all about this one-dimensional wave equation. Are there any questions? Because now I'm going to switch to multi-dimensional case. So yes, so now let us talk about the green function of the wave equation in a arbitrary dimension, in arbitrary dimensions. So as we remember, this equation can be solved using the Fourier transform. So, namely, we solve this equation that d over dt squared minus sum from I equals to 1 to d over dx I squared acting on u acting on g on green function. It is in Rd plus 1, 1 plus d. It equals to delta function of t delta d-dimensional delta function of x. So if you now compute the Fourier transform of this green function, then g tilde will equal to minus 1 over omega squared minus k squared. And the integral in when we compute this green function in coordinate representation, we first compute the integral in omega, and we choose the contour of integration such that g of tx is equal to 0 when t is less than 0. It means that we are looking for such solution of the wave equation that it depends only on the value of the right hand side in the past, not in the future. Yeah, thank you. So we need to compute this integral d k over 2p to the power d minus d omega e to the minus I omega t plus I kx over omega squared minus k squared. So and it is a multiple integral. So this integral is in Rd, and this integral is from minus infinity to plus infinity. So who remembers or who can easily find what should be the contour of integration in omega such that this condition is satisfied? So there are these two poles at absolute value of k and minus absolute value of k, and yeah, thanks. Like this. So now, if time is negative, then minus t is positive, and if we substitute omega equal to I times some big positive number, so if you are in the upper half plane, then this integration contour can be closed, and the integral equals to 0. But if t is positive, we should close this contour in the lower half plane, and in this case it will be non-zero. So there is this integral.
If we, in principle, take another function.
Yes.
So the difference between functions is in the kernel of the data.
Yes.
So this means that the residuals of this function are in the kernel of the data.
Of course, because omega square equals 2k square in this case, and this is precisely what is our operator. Because if we act with this operator, d over dt squared minus sum of d over dxi squared, if we act with this an exponential minus I omega t plus I k x, it equals to minus omega squared plus k squared times this exponential. So if omega equals to plus or minus absolute value of k, this exponential is in the kernel. So so maybe I can write this. So and we see that this kernel is quite big. There's a lot of plane waves. It's like entire R D, even two copies of it, RD, because there are positive frequency exponents and negative frequency exponents. So minus k t plus I k x and this exponential plus I absolute value of k t plus I k x lie in the kernel. It's quite big. Okay, but now we need to compute this integral. So is it fine? So and now we know that it is proportional to Heaviside theta of t. And this is so it vanishes when t is negative, and if t is positive, we just close this contour in the lower half plane, and this integral equals to I also forgot a factor 2 pi here. But anyway, at some moment I will forget about all these factors for simplicity. So here we should multiply by I, and so first we integrate in ddk, or pi to power d. And then we should multiply by I, which is minus 2 pi I over minus 2 pi. No, again, if we close this contour in the lower half plane, then we can further deform it like to such kind of contour. So no, these integrals do not so this integral comes not from this parts around residues. It's a kind of global statement. So we cannot say that this contribution is negligible or something like this, like that. It works in the in kind of the opposite way. You can say that since this contour over the since this integral, no, maybe, wait, how to say it? We can say that since this integral over the closed contour equals to sum of two residues, and explicit contributions from this integrals around residues is only one half of that value. We can conclude from that that this integral over this line is another half of the contribution. So this and yes, and as a consequence of this, we can say that if we no, I think. And yeah, we can think differently that if we choose, if we switch this contour to this one, then this integral will become zero, which means that contribution from this line without the small semicircles is the same as contribution of this semicircles, because when we change sign of this integral, then we get zero. So, okay. So here we get a sum of residue at omega equals to absolute value of k plus residue at omega equals to minus absolute value of k, and um, this function e to the minus I omega t plus ikx over omega plus absolute value of k omega minus absolute value of k. So it equals to side here. So when we take this residue, this plus, we get to absolute value of k in the denominator. And the exponential was minus I absolute value of k times t plus I kx. And if we take this residue at a minus absolute value of k, then we get a negative sign in the denominator, because it is a minus absolute value of k minus absolute value of k. So it is another exponential with a minus sign. Here it is plus I. Absolute value of k t plus ikx.
Probably there was another minus in the first integral we computed. So
Where? Why?
can you so we started with minus the omega.
Yes, so one minus was because this integral was clockwise and not counterclockwise. It cancelled this minus, and There was also 2 pi I, which cancelled this 2 pi. Mm. Uh, so, let me think. Mm. Yeah. And and now we need to compute this integral. I didn't know. So in principle, I wanted to compute it in full generality, like for arbitrary dimension. But it's a question to you. Is it fine if I start to write integrals in multidimensional polar coordinates? It's not so complicated, but uh, did you see anything like this before? Mm, mm,
Integrating the radius and then integrating the border of the sphere.
mm. Yeah, or all other angles. But maybe let me try to show this, and uh, um, in principle, it is not so complicated, uh, especially for such function. So. So we have this integral, and let us write what it is. So there is an angle between our coordinate vector. Uh, Let us say that uh, absolute value of x equals to r, and define that absolute value of k is denoted by k. Then this integral can be written as as I have psi theta and uh, to k. This is the notation for the absolute value. And here we have e to the uh, minus I k t plus I k r cosine of theta. So another notation, theta is the angle between k and x. So scalar product between k and x equals to kr cosine of theta. So it's another notation. So minus I k t plus I k r cosine of theta. Yes, so in principle, we see that so there is a kind of reference vector, which is our vector x, and there is this angle theta, which is measured with respect to the vector x, to the vector x, and so and there is this vector k. So, and we would like to integrate on this. So the good news, if you look at this integral, is that it depends only on the absolute value of k and on this angle, because in principle there are other angles like this one, but our function does not depend on them. So in principle, we can compute the integral in all that angles, and we will be left with just one integral. The only question is how to perform this integration. So let us postpone this integral for some time. And let us talk about polar coordinates. Mm. Maybe I don't know what is the precise name. Probably polar coordinates is for 2 dimensions, and for 3 dimensions spherical coordinates. Maybe it's hyperspherical for arbitrary dimension. Ah, yeah, but what is called them just polar, or maybe hyperspheric. So let me check the coordinates. So when d equals to 2, there is this picture. So uh, we have our plane, and if we want to draw an element of area of this plane, so we can say that there is some belt which is a sphere, or which is one-dimensional sphere of width delta r. Mm. And we can take such a piece of size as. So we are measuring r and angle phi. So if we take some area element of size delta r times delta phi, then its area is what? Who can tell this? So area of this on this element. What is this? Hmm?
Is delta
Mm-hmm.
times delta phi, and maybe
No, also times r, because if it is delta phi, then the length of this equals to r times delta phi.
yeah.
So this uh, uh, so it is delta phi times r. So the integral maybe well, let it be phi. So the integral of so if it is x and y, then integral of some function f of x and y dx dy should equal to the integral of this function f of x of r phi, y of r phi, r dr d phi, right? So it's for d equals to 2. So are there any questions? about this. Mm. So we can, if we want to prove this, maybe there are other ways. We can either compute Jacobian from x coordinates to y coordinates, so we can make this approach more formal and say that this plane can be divided into such small pieces of size delta r times delta phi, and then we take a limit delta r and delta phi goes to 0. But the formula should be in this anyway. So, uh, for example, if we can compute the radius of a circle using this formula, because so it is from 0 to it is of a radius r, for example. So s equals to integral from 0 to r dr, integral from 0 to 2 pi d phi, and it will equal to r squared over 2 times 2 pi. So it is pi r squared, so as expected. Mm. So it was d equals to 2. We will also need this case because d equals to 2 is one of the examples. So another case is d equals to 3. So in this case, polar coordinates look like this. So there is a z-axis, x-axis, and so z, x, y, z. By the way, we can also write a method between these coordinates. It's kind of important. So it is x equals to r cosine phi, y equals to r sine phi. Mm. Yeah, so in this case, one angle is the angle between our radius vector and a z-axis. So this angle is called theta. So this is our uh, so we might get confused between uh, k and r. So probably let me use k instead of r everywhere. Let us suppose that it is a momentum space integral. So this will be k. K dk, dk, and here also k sine phi, k sine phi. Sorry, delta k. Okay, so here there is this vector k, and the angle between this and the z-axis is theta. And another angle is the following one. We take projection of this vector k onto the xy plane, so it projects to some point. And the angle between between this projection and the x-axis is denoted by phi. So now the question: what is the mapping between coordinates? Like, who is z, who is y, and who is x? Mm-hmm. Thanks. Mm-hmm. Thanks. So it is still cosine of theta.
Yes, cosine, both
Hmm?
cosines. Yeah.
And it is to check that sum of squares of this z, y, and x is actually k squared, because sum of this gives cosine squared, and then the sum of these two, this two and this one squares, gives sine squared, sine square plus cosine square.
So what's the range of the two angles?
So you see, when we need to have all possible z's from k to minus k, that so this theta should vary from minus pi to pi, and then
Sorry. Theta is the one above k, isn't it between 0 and
hmm? Oh, so when from 0 to pi, yes, sorry. Zero is when k when z is k, minus k is when theta is pi. So and phi is from 0 to pi. Right. And now the question about the area, about the volume element in this case. So mm, we should imagine uh, such a kind of uh, such kind of boat of size d theta. Let me try to draw this. Maybe it's better to use. It's better to draw a separate picture. So, if you look at the uh, if you look at this projection, such that uh, x-axis is here, z-axis is here, and y-axis is perpendicular to the blackboard. Then this area element is the following one. So we have this. We have some element d theta. Oh,
oh, sorry.
hmm?
Probably theta should be taken be the one below k if we want this to be the parameterization, because actually theta is k cosine of theta in this case.
Oh, yes. Sorry. I missed sine and cosine. Yes.
Yeah, it depends on the angle.
Yes, but a conventional notation is this one. Uh, sorry, this one should be correct. Yes. This projection of the volume element is this one. So, uh, so it is something uh, of size delta theta here. And if we compute geometric size of this part, then it will be delta theta times times k, because distance to 0 is k. Then we also have this size, which is delta k. But we'll come to this question in a second. Um, because what is drawn here, so we should look at this now from the other side. So it's kind of section of this picture, but if you look at the three-dimensional picture, then it looks like this. X, X, Y. So we have here this um, this belt. So it's kind of external part of this. It also has an internal part which should be drawn somehow like on this. So it is this thick belt with the area of its section given by this expression delta k times delta theta times k, but it also has length, and so the length element is equal to, so there is a kind of a radius of this belt, and it is given by r times sine of theta equals to k times theta, k sine of theta, and so finally the volume element is given, delta V is given by this area element delta K times delta theta times K. This is one part, and another part is that we should multiply this K sine of theta by delta phi. And because and it equals to the length element of this belt orthogonal to this section, because like this. Is it fine? Yeah. So it can be written now in differential form that dv equals to k squared dk sine of theta d theta d phi. So it is for a three-dimensional volume element. And now let us move to higher dimensions. So are there any questions about this computation? But did you see it at some moment or not? Was it at some class? Ah, yeah. So now let us see what happens in the higher dimensional case. So in this case, I will not draw pictures, but we'll use an analogy. So let us consider d equals to 4. Mm. So first coordinate, let us call it k4, will equal to k cosine of theta 3. Then k 3 will equal to k sine of theta 3 times mm, mm, let me think for a while. Mm, cosine of theta 2 k 2 will be k sine theta 3 sine theta 2, and k1 will equal to k sine
Shouldn't be also cosine of theta 1
uh,
in that
sorry it's
in K2 we should have K sine of theta 3. Sine of theta 2?
yeah. Oh, thank you. Cosine theta 2.
No, no, sine of theta 2, but also cosine of theta 1.
Yes.
Yes.
Thanks. And this one will be a sine of theta 3,
Both sides. Okay.
theta 2.
Sine of
Mm, uh, do I like this? So uh, so it looks like this. First one is cosine, then this first one is also a cosine. Yeah, in principle, yeah, it is fine. So it's kind of a nested procedure. Uh, Maybe I don't know. Mhm. And and now what happens with our computation? We first draw a plane with a plane corresponding to the last coordinates, k2 and k3, or k4 and k3. So this is uh, k3 and k4. So here this uh, is this a volume element or area element which equals to again delta k, and here it is delta k. Here it equals to k and delta uh, delta theta 3. And mm, uh, if we fix k4 and k3, if we fix theta 3 and absolute value of if you fix absolute value of k and theta 3, then what we get? All these terms are fixed, and we get some sphere of radius k times sine of theta 3. So this four-dimensional volume equals to k delta k uh, delta theta 3 times dv2. It's a element on its area element of something two-dimensional parameterized by the angles theta 2 and theta 1. But the radius of the sphere, we can see it from here. It equals to k k times a sine of theta 3. And it will be given precisely by the previous expression. So this theta 1 is a coordinate on a circle, so this measure does not depend on it. And this measure will equal to what? It will be, so in this first part, k delta k delta theta 3 and this is multiplied by k sine of theta 3 squared times sine of theta 2 delta theta 2 times delta theta 1, because so it's a volume element of this smaller sphere, right? So it has dimension by 2. And if you continue this inductively, then it is clear what happens. We will get the power of so if this was originally 5-dimensional sphere, or if it was a 5-dimensional space, we would get here not power of 2 but power of 3, and here we would need to write this a kind of area element. So if we can continue this induction to arbitrary d, then it is dv n equals to k n minus 1, or d minus 1 dk sine of theta d minus 1 to power d minus 2 d minus 2 sine of theta d minus 2 to power d minus 3, and so on to sine of theta d theta 2, and then product of all d thetas, d theta d minus 1, and so on, d theta 1. So the volume element of a sphere. And in principle, one way to compute the volume of a sphere is to compute this integral, but maybe it's not the best way. Are there any questions about this formula?
So the angle that not appears in the volume variant is the only one ranging from 0 to pi, and
Yes.
the other from 0 to pi.
Yes. Yes. The last one is a kind of cyclic angle, so changing of this angle does not change anything. So in this rotation is symmetry, but other angles affect something. So this kind of spherical rotation symmetry is essentially broken. And the only remaining symmetry is rotation in this like rotation around the first n minus 2 axis. Okay, so we have this formula, and let us apply it now. So we see that this integral, which we want to compute, depends only on the first angle. And the integral in other angles can be computed, and we will say that it's just some number. Area of d minus 2-dimensional sphere of unit radius. So there is that integral, and I continue it here. So this integral equals to I here beside the theta of t times s d minus 2, and this integral in s d minus 2 over pi to power d, and we have an integral in k, k d minus 1 dk, then sine of theta to the power d minus 2 e to the so integral in theta is from 0 to infinity. Integral in k is from 0 to infinity. Integral in theta is from 0 to pi. So now we have minus I k t plus I k r cosine theta minus d theta e to I k t plus I k r sine of theta over to k. Okay, and now let us write this again. Let us denote this by some number CD, or maybe even 2 CD. So it will be CD beside theta of t integral from 0 to infinity k d minus 2 dk, integral from 0 to pi sine of theta to d minus 2 d theta, and so now we can make the following remark. So let us first write it as is. IKT plus IKR cosine of theta. So now the following remark. In principle, so we are integrating in theta, and it goes from 0 to like it is approximately 0 and like minus epsilon. So it is theta. It changes in this range, and we can notice that there is the following symmetry. If we change theta to pi minus theta, then it is a one-to-one map. In the sense, we have a symmetric point for any point corresponding to angle theta, and what happens under this replacement? So sine of theta maps to sine of theta. So measure is positive and it does not change. But cosine of theta maps to minus cosine of theta. And it is clear from this picture, because here there are positive values, here there are negative values. So cosine of theta maps to minus cosine of theta. So this means that we can make this two exponents almost the same, because here we see we had a difference of these terms. Here it was plus. We can make both of these terms equal to e to this expression and e to minus this expression. So we can change the sign of cosine of theta in this term by reverting the order of integration in theta by applying this symmetry. So let us apply it to this. Let me think. To the first, or maybe to the second term. Let us apply it here. So if we apply this symmetry here, then this integral can be written as I CD sine theta of t, integral from 0 to infinity, k d minus 2 in the k, integral from 0 to pi sine of theta d minus 2 d theta, and here we have difference e to the minus I k t minus r sine theta, and here we have e to the minus I. Here we have I k t minus r cosine of theta. I'm doing all this because here we have integral in k, and in principle we could rewrite this integral in k as an integral from minus to plus infinity, right? Uh, uh, because this exponential and this exponential have opposite signs, so in principle we can they have the same factor here, but opposite sign in front of k. So in principle we can say that they might come from the integral from different parts of integral, for minus for negative case of positive case. Of course, it depends. So, yes, precisely. Uh, but let's try to play this game. Mm. So, probably I will not have time for both cases, but let us try. So, if we want to write this in the uniform way, uh, so let us write from minus infinity to plus infinity. So if d is odd, then this change of measure gives precisely what we want. It gives this integral. And for even k, we should insert some signum of k. So the general formula will look like on this, like integral from 0 to pi sine of theta to d minus 2 sine function of k to power d minus 1. I think e to the minus I k t minus r cosine of theta. So we get this integral. And in principle, we see that this should be so when d is so let me think. Hmm?
I'm not sure if this gives the desired result where d is even. Shouldn't it be e to the minus I k t minus r cosine of theta plus sine of k to the minus 1 plus 1 times the other exponential, and then it vanishes for d odd?
No, what do you mean?
In case d is even, there is no the integral from minus infinity to plus infinity does not give a single term. It seems to me.
Uh, no, but this sign function of k, which gives so when k is positive, we get this term. When k is negative, we get this term with minus sign because of this sign,
Okay.
right? Mm. Mm. Hmm? Mhm. Yes. But we first change from pi to 0. So it's integration range for this new variable. And then Jacobian of transformation is minus theta. So we can remove overall sign coming from the Jacobian and change the range of integration back, right? Uh, so. mm, So what else? Uh, uh, the easiest way to check such things, to check the signs, is to try to integrate some function which is definitely positive, and the integral after the change of variables should remain positive. Mm. Okay, so now we need to compute this integral. Uh, mm, Actually, uh, uh, maybe let us first consider some special values of d. For example, let us start from d equals to 3. So where should I raise something? Maybe this. So when d equals to 3, so I will not write this term. So it is integral from minus infinity to plus infinity. Uh, uh, k dk, integral from 0 to pi, sine of theta, e to minus I k, e minus r cosine of theta. Hmm. Actually, mm, sine of theta d theta. Yes, so this integral of in sine of theta d theta can be written uh, k dk. This integral can be written as integral of d cosine of theta, from -1 to 1, e to minus ik t minus r cosine of theta. So let us first integrate this integral in the angle. So it is e to the minus I k t minus r minus e to the minus I k t plus r divided by minus I k plus yeah, it's true. Thank you. And so now this k cancels. Maybe let us keep this I sin d theta h of t. So this I cancels, this k cancels, and we get the integral for the delta function. So it equals to 2 pi times c3 times where
the denominator.
ik yes, thank you. The theta of t, and here we have a difference of two delta functions, delta of t minus r minus delta of t plus r. So since time is positive and radius is also positive because the distance to 0, this second delta function does not play a role, and also divided by r. So the only surviving delta function is the first one. So it equals to mm, 2 pi beside theta of t delta of t minus r over r. So
The delta comes from the inverse radius from 1.
yes, it's just integral of this exponential. Yes. So mm, So are there any questions about this computation? So mm, 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 mm. So mm, so, I don't know. Uh, maybe it's better to postpone the other computations for the next time. What do you think? Because actually there are some tricks which I uh, already forgot, and it may take a little bit longer. Uh, well, and it is only 5 minutes. So, so
Is that minus r is that getting a solution where we convert the
yeah. So let us write this. So we want to solve an equation. The Lambertian of u equals to some function which depends on t and r uh, of t and r. So looking at this green function, it is given by the integral of so we want to write a solution u of t and r, and mm, we can imagine that we already computed the integral in t and used this delta function. So then the remaining integral in r will be the following: d3r prime uh, 1 over r minus r prime uh, f of t minus r minus r prime uh, comma r prime. So, and it is called a retarded potential. So the meaning of this formula is the following. If we want to compute the solution of this inhomogeneous wave equation at some point r prime, or at some point r, sorry, uh, we need to imagine that there was some wave which was emitted at a point r prime at the moment of time different precisely by the distance between these two points. And this wavefront reaches our point of observation decaying by the law of 1 over r. So it is a kind of Coulomb law, but with time dependence. So So if, for example, f was t independent, then it would mean that u is also t independent, and this function will be a green function of three-dimensional Laplace operator. But if you go to the wave equation, the only effect which happens in three dimensions, and actually in all odd dimensions, is that now we should take this retarded potential. We should take into account that the value of function only at time shifted by r minus r prime. And this is the case for odd dimensions, and for even dimensions, it will depend also on f in all other points. So, yes, well, not yes, it's edible. So So if we think that it is, for example, equation describing sound, and we apply some, we emit some sound at some point, at some moment of time, we will see such kind of wavefront which increases, goes to infinity, but there is nothing, of course, there is nothing in front of this front because waves travel with the speed of sound. But the point about even dimensions is that there is nothing behind this front. It is. It has a sharp begin and a sharp end. So if there is no sound after some moment of time, then this then everything goes to infinity, and the solution will be zero. So. And this is why we can speak and we can understand each other. Because if we lived in two dimensions, there will be a lot of distortions. So any phrase would contain the infinite time tail. Okay, and this will compute the next time. Okay. Probably I'll have some problem about this function. Okay, thanks for your attention.
So we had an example of wave equation where we have non-zero but a function that depends only on t and the radius. Or is that false? No, not only on the distance. It could depend on each of the variables that are positive. Okay, nothing. Okay, I read it.
My example was about a t-independent function, for which it reproduces the given function of Laplace. Welcome.